the maturely immature Orientale impact basin.
Thanks. Okay, so I'm going to tell you a little bit about some of the work I've been doing lately in regards to maturity with a bunch of different data sets back from LRO, as well as some of the data sets we've taken from Lunar Prospector and Clementine. Bear with me, I'm going to start out kind of in a global sense, and eventually I'll get back to Oriental impact basin towards the end. So in 2002, Jeff Johnson took a look to see if the Lunar Prospector epithermal neutron data could be related to maturity in any way. And this is a comparison that he made in his 2002 paper between OMAT and epithermal neutron counts. And while he saw what he interpreted to be a moderate correlation, there really wasn't as strong of a correlation as he had hoped. Now, I want to make clear that this was for the global moon, so that becomes important as we move along. So recently, Dave Lawrence in 2015 decided to take another look at it with Lunar Prospector. And so he took a look at a few things. He took a look at albedo in the form of Clementine. Yeah, that is whack, but he actually looked at Clementine. Optical maturity parameter of Lucy's Clementine data. As well as the Diviner-Christensen feature, which we've all known for quite a while that it varies with iron and titanium content, but a more recent discovery by the Diviner team is that it varies as well with soil maturity. And so Tim in the last session was talking about correcting this in order to get rid of it, to concentrate on composition. Like, don't take it away. Hopefully they don't deliver products that way. So here's a look at what he did. I've recreated this in the process of doing this study. So this is the epithermal neutron counts from Lunar Prospector relative to optical maturity. And the approach he took was a little bit different in that he decided to discard the poles, thinking that those counts could be attributed to water ice. So everything plus or minus 65 degrees is what we're looking at in a non-polar sense, as well as he removed things that could, areas that could interfere with the hydrogen signal. So he removed the creep-bearing regions for the time being. And so if we're looking at this, so this is the whole moon in the gray dots, and in the light blue dots is the non-polar creep-bearing terrain removed data. And so this is basically your non-polar highlands relative to the whole moon. So as you can see, there was quite a bit of scatter as was in the previous look of Jeff Johnson. But as we look at primarily the non-polar highlands, this starts to become quite a bit more trend-worthy, I suppose you might be able to say. Taking a look at epithermal neutron counts relative to Clementine albedo, there's even a more apparent trend, even at a global level. Kind of goes back to what Tim was saying about there's an albedo effect between data sets. Well, it seems to be interesting that it seems to also be relative to epithermal neutrons as well. And here is the CF feature wavelength. Everything kind of flips here. So shorter wavelengths are more immature, more mature things are at longer wavelengths and relative to epithermal neutrons. So he took these epithermal neutrons and decided to make these hydrogen maps, which you can see here. And he made this key interpretation that suggests that the bulk nonpolar hydrogen is attributed primarily to space weathering, hydrogen implantation. So a lot of these higher areas are have increased hydrogen abundances, whereas some of what's interesting about this is that younger, more immature areas will have these low hydrogen abundances. And so you can see these little hydrogen depletions correlating with immature areas on the surface of the moon. And older, more mature areas, so areas that haven't been as cratered, will have higher hydrogen abundances. But it's interesting, and I'll touch on this later, these higher hydrogen enrichment areas in the nonpolar context will tend to be a lot more locally located in a lot more smaller of an area compared to these hydrogen depletions. So I started talking to David, and we started thinking, well, we kind of should check where these hydrogen depletions are and what's going on. And so I've gone through and with an intern, and we started taking a look at some of these areas. Some of them stick right out. So Tycho, there's Orientale, King Crater, Tsiolkovsky, and quite a few other areas, Jackson Crater, Clavius, etc. And what's interesting about this is that a lot of these hydrogen depletions, while we have these trends with optical maturity and albedo, some of them don't seem to make as much sense. So Tycho definitely makes sense. It's Copernican crater, relatively recent. It has a high albedo, and this is Lola normalized albedo, which we also took a look at. But Orientale, for instance, is kind of blends in with its surroundings, and in maturity it does to a certain degree as well. However, in the hydrogen maps, it just kind of sticks out. It's this very apparent hydrogen depletion, which suggests that it's a very young area. However, Orientale and Tsiolkovsky, they're some of the oldest areas on the surface of the moon, even though they're younger basins and craters. So this was a peculiarity, but as you can see, as we're going into the CF feature, some of these things start popping out again. So we start thinking, well, perhaps this is in a way a sampling depth effect, because certain wavelengths you sample a little bit deeper in regolith versus, so say epithermals versus the thermal wavelengths. And finally, what I'll get to is radar. So radar has often been used as a proxy for maturity. This is a good diagram by Catherine Niche and on the MinERF team, where the optical descriptions she's showing of some Mercurian and lunar craters are shown on below, and you have S-band radar up above, and you can see how they're degrading with age, and while they look different, they are doing it in a rather systematic way. So I decided to take a look at the hydrogen maps relative to S-band radar. And here's the LRO's MinERF S-band radar global maps, which have been pretty cool to have, considering we were only supposed to collect perhaps as much data as could fit on a thumb drive. So it's pretty neat to have a global data set. So I related to the epithermal neutrons relative to the circular polarization ratio, which is just the same sense scattering relative to the opposite sense polarized scattering returned to the radar. So areas of higher CPR will be rough, have higher degrees of roughness, but you need to be careful because in the PKT and areas with higher titanium, the signal can be attenuated. So you have to look at those a bit more closely. So, but in the context of this, since we're excluding PKT in areas with greater than 1 ppm thorium, a lot of that effect is removed. And so with epithermals relative to CPR, we'll get much the same effect as we did with, say, optical maturity, where we have a decent cloud, and then when we go to the non-polar highlands, it starts to get a little more correlated. We can take a look at this a little with Imkai, and this kind of separates some of the scattering properties a little bit more. In particular, kind of separates double bounce, backscatter, and the depolarized signal. So if you go back and forth, you can see over here, say, South Pole Lacan has high backscatter. Orientale has high backscatter, but when you go to Imkai, there are definitely differences in their backscattering properties. So this is volume scattering relative to epithermal neutrons. Again, we have a decent trend. And then this is double bounce in comparison. So now that we took a look and took a little bit of stock of some of these anomalies, I decided, well, if they're correlating with maturity, we can often relate this to relative age. And so I started taking a look at some of the ages. And initially, because of how coarse some of the epithermal neutron data is, it was a little bit difficult to say, well, what exactly is responsible for this anomaly? And so this was kind of a first draft that I showed at LPSC. And we almost had two different populations where we had these lower hydrogen depleted areas and some of these higher hydrogen enriched areas. What I've found since is I've taken another closer look at this, and a lot of these higher hydrogen enrichments aren't really necessarily associated with these craters. They're nearby, and like I said before, they're pretty localized, so I can zero in on them and decide, yeah, more or less they're not really associated with these craters. So in a way, I don't really have great ages for these at this moment. So I'll have to get back to those another time. But I also took another look at down here, and so this is what I came up with. Okay, so hydrogen and parts per million relative to lunar geologic period. As you can see, we have a little bit relative hydrogen enrichment with older areas, whereas where we get more Copernican and Eratosthenian craters, we start getting less and less hydrogen that's actually been collected in the regolith. This isn't without its standouts. Clavius is obviously peculiar compared to the rest of them. But in a general sense, some of these could be a little bit back and forth in the x-axis as well in terms of their age. So, but this was pretty interesting compared to the previous results I had. So I also took a look at optical maturity just to see if everything was kind of going the same way. And yes, things get higher optical maturity as they get younger, so they're fresher and more immature. And one of the interesting things that I'll get into next as I go into Oriental stuff is some of the differences between the background hydrogen and the depleted hydrogen areas are more pronounced relative to areas that you're observing with optical maturity and other data sets. And I'm not exactly sure why that is as of yet. So here's Oriental. Sputus has really recently taken another look at mapping the area. Maunder Formation is in the inner, within the inside Mons Rook, and the Mons Rook Formation out here between Mons Rook and the Cordillera region. One of the key things that Paul mentioned was this Moore 1974 study where he lumped the two formations together, even though they're shown discretely here. And he thought there were a lot of similarities between them in which dominantly was interpreted to be as a result of just massive amounts of impact melt. And that's will be pretty important in just a moment. So here's a closer look with the hydrogen maps of Oriental. See, it stands right out relative to some other data sets. My co-chair is rock abundance maps. It's interesting because Oriental almost blends right in with the background with a few exceptions down here in the southwestern part. Relative to optical maturity, this is for context moving into radar next. So this was the same initial plot, epithermals relative to OMAT, and I put in green here everything in the area of Oriental. Now, in the next one, I just went with the anomaly here, and you can see how in maturity and epithermals, the epithermals are high, but maturity still kind of is in the mature area relative to the rest of the global moon and the nonpolar highlands, which is kind of what we're used to seeing. However, if we take a look at S-band radar, we have some similarities that become apparent. So we have the hydrogen depletion and the epithermal neutron enrichment and counts shown by Lunar Prospector. And then we have this high CPR signature for Oriental that is, both of these are unusual compared to the other data sets. And so begun wondering, well, why exactly is this? We kind of knew that, we've known this for a little while with mini-RF data. We still weren't exactly sure, but when we saw this result, we started coming up with a theory. And part of it might have to do with a sampling depth effect. Both of these are sampling more than the immediate surface. So with Lunar Prospector, epithermal neutrons, we're talking about upper 10 centimeters or so. With radar, we're talking centimeters to about meter and a half, maybe at most. So we're definitely sampling things that may still be relatively immature just in the upper regolith. And the other aspect comes back to impact melt with this interpretation by Moore. If Orientale does have this predominance of impact melt, there are a few flow lobes that one might interpret it, but a lot of them have been degraded away as seen in optical maturity. Then perhaps we have a predominance of glassy materials. And if that is the case, hydrogen would have a way of not being able to stick around if we have this predominance of glass. Glass tends to be hydrophobic in a way. I'm coming to understand that this is compositional dependent, so this is kind of a working theory at the moment. So I'll be talking to Carl down the hall at APL a lot more. So I think I need to wrap up. I'll just leave this up. Thanks for your time.